Okay, so let's start again with a second hands-on session. I know that maybe you didn't have time enough to finish your hands-on sessions of the first tutorial, so I would recommend that you try when you are back in your hotels or, or anyway, when you go back to your place, and eventually if you have questions, you can always contact us. Okay, so I think that we have a short amount of time. There are many people, so we can address all the questions probably. But I mean, just keep on trying, and we are here to help you out. So the second session is presented by Lorenzo Monacelli from the EPFL in Lausanne. And okay, Lorenzo. So he will, I think, help you out to set up like automatic calculations using clusters.
Okay, thank you very much for the introduction, Jon. And now we are going to do an actual real calculation. In this hands-on session, you find in the PDF, this is the Hands-on-session2. So if you all have the documents in front, it's very good because I'm going to just follow through and explain everything that is going on. So we are going to study a system which is a real case system, which is H3S, and a strongly anharmonic high pressure hydrate, which happens also to be the second highest superconductive system we know. And so we start in the files that you should have downloaded for this hands-on session. We already provide the harmonic phonons, which have been computed. You can see them. Let me clear. And so if we list all the phonons here, you see this DIN H3S harmonic. These come from a quantum espresso calculation. And actually, I think we have also how the calculation can be run, which is, let's have a look to the quantum espresso files. So this is the standard. I don't know if most of you are familiar with quantum espresso. It's just a program to do density functional theory calculation. So this is ab initio. And in this calculation here, these input files just set up how to do a standard self-consistent calculation, so no relaxation in this case. And you have a lot of parameters, which I'm not going to explain because this is not a school of quantum espresso. So you can, most of these things can be translated in other programs if you want to use them. We put the input file so that this is how, starting from 0 to scratch, actually not 0, just the structure, the HPSS structure, which is written in these last lines of the file. We have the cell parameters written in angstrom, which are actually the primitive cell, and the position of atom of H3S atoms here. And this is just a quantum espresso calculation. You should run this file here, and then with daspw.h minus I H3S. I'm not going to run this because it will take a bit of time. And this will run the standard quantum espresso file. And then to do the phonon calculation, we have the second one, which is H3S.FHI, which is telling in this case to save the dynamical metrics in this file here, and you have the Q mesh here that we want to do. So we are going to do a 2 by 2 by 2 supercell SSCHA calculation, which correspond to a 2 by 2 by 2 mesh sampling of the Brillouin zone for the phonon calculation. So the starting point for the SSCHA in this case is a harmonic calculation that can be obtained in this way, and we have the results in these DIN HTS harmonic files. So if we open the first one, we contain, you see they are much more complex with respect to the gold one you see in the last tutorials, and the reason is that we don't have any more 1 atoms in the primitive set. We have 4 atoms actually, so we have a lot of, the dynamical matrix are usually quite good, and we have also a lot of phonon frequency for each Q point. Now the first one is only gamma, and the other files you see D harmonic 1, D harmonic 2, and D harmonic 3, which contains the other Q points, which are irreducible Q points of the 2 by 2 by 2 mesh in this system here. So, first, we want to try to we want to do in this tutorial here a manual calculation. So we want to see a bit how SHA was run in the early days, and this corresponds essentially to how to run so how to run each step of the calculation separately. So if we look at the full all the frequency, so we ask the frequency of the harmonic calculation. Let's ask all of them. They are quite a lot. So these are all the frequency that appears in all the files. And as you can see, we have some frequency which are negative, which means imaginary, and some frequency, and we don't have any frequency which is 0. We should have at gamma the lowest frequency to be the acoustic one, to be 0. So this is a standard problem when you do harmonic calculation, and if you don't use a very high cutoff or very well converged parameters, you will not see acoustic phonon goes to 0. In this case, these are the acoustic phonons. And the other part, we get imaginary phonons. This is not a problem of our parameters which are not well converged. This is actually true. So this system is an high symmetry structure, which if you don't include an harmonic effect, actually is a saddle point of the Born-Oppenheimer energy landscape. So as Jon and Francesco were pointing out this morning, is a system in which harmonic calculation fail. Okay, so we need a way, if we actually want to start doing a SHA calculation, simply importing these materials. So if I, for example, can I use a Python here? Unfortunately, no. So let's do it manually. Then, so if we want just to load these phonons, like, we can do like this. So we can import cell constructor, which is the main actual module which is dealing with phonons. You usually load as CC and then cell constructor dot phonons. We can try to load the phonons, which is done in this way. You have, in principle, done this in the last tutorial, but I want to do it manually so that you can see exactly what each command is doing, which I think is important if you want to use then the code yourself when you go out. And we can see DIN, how was it called? Let's go to the tutorial. How was it called? Let's just copy this here. So, okay. We remove the final one because we want to give this this file only the root file name of the dynamical matrix, and then tell how many irreducible points we have, and then, for example, we can diagonalize this dynamical matrix in this way. Oops. So it's din.diagonalize supercell. And if we do like that and we print, and we have diagonalized the font. So if we want to extract a random ensample, we cannot because we have imaginary phonons. So how do we extract a random ensample? We do it like this: import SHA.ensemble, and then here we create the ensemble, which is SHA.ensemble, and then we pass the dynamical matrix, and the temperature we want in this case is 0 Kelvin, since this is a quantum material, and then ensemble.generate, let's generate 100 configuration. So if we now try, we save this data, let me just keep it open, and so we try to run this file, we should see an error. And so the first error that we see is that we cannot extract because we have imaginary phonons. So it says the current matrix is not positive definite. So we need to force the dynamical matrix to be positive definite. And to do that, we actually, there is a very nice method, which is just din.force positive definite. And this is actually just flipping the frequency that were imaginary to frequencies that now are finite. So this is not a very meaningful dynamical matrix, but we don't care because we just need an initial condition for the SHA. So if we now run, we see another error. No, we don't see error. That's very nice. Okay, so anyway, that's not all we should do. So for example, if we save the dynamical matrix like this, din.save QE, which stands for quantum espresso format, and now we see this is my dynamical matrix. If we do like that, and we save and we run, again, now we have the last files, which are my din, and we can inspect these files. And if you look at the frequencies, now we don't have any more. Let's do what we did last time. So my din all. So now we don't have any more imaginary phonons. That's very good, but we still have these optical modes which are wrong. And if you try later to run, or the acoustic mode, which are wrong, if you try later to run the minimization of this, you will incur in errors. And so we must also somehow fix this problem. How do we do that? We need to impose symmetries, through which among the symmetries there is also the acoustic sum rule. And to do that in the SHA code is simply din.symmetrize. So if we add also this thing before the saving, and now we rerun again this script, and we grab the frequency, no. What happened? Why is not 0?
You didn't save.
I think I didn't save. Yes, that is true. So if we run again, yes, as you can see now, the frequencies are almost 0, not numerically, because I mean there's still noise in the numerical diagonalizations, but we have now imposed acoustic sum rule, and this is a good starting point to which we can start now running the SHA. Okay, so let's go on. So this is very manual. So what we also did here, after this line here, we generated the ensemble, but the ensemble is just lost in the memory of the computer, because we never actually saved this ensemble. And now we can save the ensemble, and do ensemble.save, and we can give a name of a directory. So for example, let's call this data, and we can give the name of the number of the population, for example, I think 1, and I will tell you better what this is. And if we just now run this once again, okay, let me clear. So maybe I can zoom a bit so that, yes. So you can see a bit better, I hope now. So actually now we generated a lot of more data. There are a lot of more dynamical matrices here, which has just this start and population 1. These are exactly the same dynamical matrix we generated before, which is the dynamical matrix used to generate the ensemble, the one with the start. The end one is the final one, that in this case, since we didn't do anything with this ensemble, are exactly the same. And then we have also the data directory now, which contain a lot of data. And now inside this data, if we want to see, for example, what is the SCF population 1, let's take the first one, 1.data, this is actually a structure in the supercell, which is exactly what one of the structure in our ensemble, and we can visualize it. How? Let's go back here. So let's actually And we can actually import ASC, visualize, and now we can do ASC, visualize, view, so that we should be able to see the structure, and then ensemble.structure. And this is a list that contains all the structure. Oops. And we can now select, for example, the first one. But this is a cell-constructor structure, so if we actually do this, you should see an error. Let's try again. So, yes. And the problem is that the structure which is inside the ensemble is a structure of kind cell-constructor. We are asking here ASC to actually visualize the structure, so we need to convert to an ASC atoms, which is like get ASC atoms. So now if we do like this, it should not error anymore. Very well. So why did
you didn't remove the first line?
Yeah, sorry. So exactly. So this is actually the structure that we have. Now I can rotate it. And so you can visualize this structure is defined in a 2 by 2 by 2 supercell, which is actually what we get from the atoms. The atoms are not in a asymmetric configuration, are displayed. You cannot see very well because this is at t equals 0, but we can actually artificially enlarge a lot the temperature, and the temperature is defined here in the last, so let's put 2000 Kelvin, so we will see something very nice. And if we run this again, yeah, you can see that now, I don't know how much you can see it, but still the atoms are not in the asymmetry. So configuration, they are actually displaced in a random position. And so now that we have the structure, you see so inside the data directory, actually, we have all the structure which are put here, and all of them are actually, this SCF file contains the structure as I was showing before, SCF population 101, for example. This is in a valid quantum espresso format, so you can use whatever program you like to generate input file for that program, do ab initio calculation, and then what is actually interesting here is that you should get so you should save the output file so you should save energies and forces in the respective file. So for example, if I go now into data and into energies, so this file here contains all zeros. These are the total energy in Rydberg of all the structures, which we have not computed the energy yet. So it's 0 for everyone. We should fill this file with the correct energy once we have done the calculation, the initial calculation. And we have also, they are not saved here because they have never been computed, but we should also compute another file which is called forces underscore population 1 underscore the index of the configuration dot, which contain the forces in Rydberg over bar, which is the standard form of quantum espresso. Now, this can be done with whatever program you want, and this is very manual. I mean, the code was completely automatizing this in the last tutorial, doing everything from just automatically, but you can do it manually if you want to interoperate with something which is not interfaced with ASC, or if you want, for example, do some calculation with a cluster with a non-standard, with your own program or some non-standard things. So, and that's how things are done. So if we actually let's say that we want to generate input file for quantum espresso. So we have this, I provide this script input file of ss.sh. So since, as I show you, all the SCF files contain the structure already written in the Quantum Espresso format, what we need to generate an input file from Quantum Espresso is simply to attach an header, which is, for example, in this case, saved here. This is a bash script. Don't know if all of you are familiar, but it's a very useful thing if you want to manipulate files and these kind of things. So what this is doing is just taking the data, the population, and generating the input files for Quantum Espresso. So it's looping over all these SCF population, my population, and whatever file. And for each one of these files is generating an input Quantum Espresso file, which is obtained by copying the header, the Quantum Espresso header, which is in common for all calculations, which contain the parameters, into that file, and then by just attaching the structure to that file there. So if we run this calculation here with bash generate input file, so what it happens is that inside data we have input files population 1. It's like that, and you have all the input file of Quantum Espresso. So let's take one to look at it. So for example, this one. And so these things that you see here were just before the cell parameters, is just the header file, which is in common for all of them. And on the bottom of this file, we attach the structure, which is the structure that the file that I was showing before. And so that's it. So we have now all the Quantum Espresso files. So if we want to do something very boring, we can run Quantum Espresso for each one of them. And it will take, if I do in this computer, a lot of time. Or we can copy all this file on a cluster and run the calculation there. And then copy the file back. So let's say that we did like that. And so I should have the output file of Quantum Espresso saved here. Now, this was done only for 10. I've done for much more. So let's regenerate everything just with 10 structures so that we have all the files. I think it should have already the input. Yes, it should be this generate ensemble. So if you look, this is exactly what I was telling you beforehand. This is done at 300 Kelvin. This is exactly the same file I wrote you before, but with 10. So we can simply put here on the top here just. So we fix the seed so that all of us will have exactly the same mp.random.seed equals 0. So this time we will have exactly the same random ensemble, all of us, because we are using the same seed. And instead of generating, so we will use a temperature which is 300, and we generate only 10 ensemble. So if we now remove data, SCF, population 1, all of this file, and also energies. Okay, and now we reload, we re-execute this program again. Now we should have into the data directory only, why are they 30? No, they are 10, not 30, sorry. Ah, yes, because I didn't remove the U population, sorry. These were not being removed. So let's run again. And yeah, we are always looking to this configuration. So if we look now inside the data directory, you see only 10 configurations. Now we let's say that we have the output files of our Quantum Espresso configuration that we already computed by copying them in a cluster. And you want to run a SHA calculation with them. So how to do that? We need to prepare some files. I think I should have here a script. Yes, it's this get energy forces, which is this is another bash script, which is very simple, and the only thing that it's doing is looking to the directory. Here we have the number of atoms and cycling of all the configuration, and he just extract from each file, from each Quantum Espresso output, the information we need. This line here is exactly the energy. So in Quantum Espresso, the energy is written in a line which starts with an exclamation mark. So we only select the line that starts with the exclamation mark. And I can show you this very quickly. So let's close this file. And let's go to the Quantum Espresso output just to have an idea of what's going on. So if I do grep exclamation mark structure 1.pwo, so we extract only the line that contains the total energy from the output file. And in this way, we can select this line here and copy it into the, it is this line here, we copy it into the energy file. Then we extract the forces, and so if we run this line here, it's actually, so if we grab the force, we see a lot of information, actually. So as you can see, we see the force for each atom and some other information which we don't care about. So we can actually select these forces, which is the force that acts on each atom, and copy this in another file, like it's doing this file here, in the force file, which is called forces underscore population 1. And we can do exactly the same with the stress tensor. So if we grep total stress to, for example, this stratum1.pwo, and we select the three lines that follow this, we have the stress tensor written in Rydberg over bar here and in kilobar there. So we need the one in Rydberg over bar in cube in the SSCHA files. So if we now run, here we run this file, so dash get energy forces, we have, and we look at the data directory, we have forces, pressures, and also energies of the system which have been computed. Okay? So this is very manual. So this is how the SSCHA minimization were done in the very early days. Now it's possible to do all of this automatically, but I think it's good to do this manually at least once to have a very clear idea on what's going on under the hood. And this is actually a way in which you can also hack the code if you want, because you can see exactly how things are going on under the hood. Now, we have computed the ensemble, we have done everything, we want to run a SSCHA minimization. How to do that? Now, let's open again, so let's copy this load file, and let's instead, write this file again. So, run minimization, let's call it. And we are going to do that live. So we import the modules that we need. So import cell constructor and the phonon modules. We load the SSCHA, the ensemble module, and the minimizer module. And I think that should be the case. Now we load the dynamical matrix, which simply is phonons. Now this is the dynamical matrix used to generate the ensemble. When I save this, is this one, din start population 1. So din start population 1 underscore, and then the number of irreducible Q points, which in this case are 3, because we have 3 dynamical matrices. So you notice that I'm not putting the last number because we want to load all of them. So not just the first one, we want to load the first one, the second one, the third one. So I put the root of the name and then the number of points that makes this dynamical matrix. So I'm loading all of them in this way. And now I'm loading it. We want to load the ensemble. So ensemble is an object which is SHA.ensemble, and we initialize ensemble with the dynamical matrix at the correct temperature, which was 300 Kelvin in this case, and now ensemble.load. So we need to tell him the data directory, which is the same as before, the population number, which is 1, and the number of configuration, which was 10, if I remember correctly, the sequence of arguments. Can also be called by keyword, but I don't remember them, so let me try to see if this doesn't error. It's erroring. Why? Let's have a look to this data. No.
The shape of the array are different.
No, yes, the problem is that it didn't copy the pressure. Okay, I think this was a bug. Okay. So I think this was updated, but eventually not. So it was a bug in the get energy forces. I think somehow here. This file here, yes. It do not contain the printing the tree line. So this was something that was not updated. So if now we recall again this file and we check the pressure, it contains the pressure. Okay. So now run minimization should work. Yeah. So it's correct. So what I did is that in that script I missed the fact that this minus R3 that I added, let me show it to you again, so you can get it, get energy forces. So this minus R3 here is printing the tree line after total stress, which is where the stress is contained. And without that is a bug because it's not showing the stress. So that's was. And now that we have, we are correctly loading the ensemble. So now that we loaded the ensemble back into the SHA, we can start the minimization. How to do that is let's create a minimization object, which is SHA.ensemble. SHA minimizer .SSCHA minimizer. And then we need to pass the ensemble to this object. Now we can just initialize and run. And like that, if we do like that, we now have the minimization which is running, and this is exactly how it was in the previous. We are doing manually everything which was done not manually previously, and done. So this did the minimization, but nothing was saved in this case because we didn't ask him to save the results. As you can see, the minimization here stopped because according to our input criteria, you're out of the stochastic sampling. So this means that the reason why the code stopped is because it went out of the stochastic ensemble. Now, this manual way doesn't know how to submit a new ensemble of calculation, so it just stops here and don't submit anything else because we didn't teach the system how to do that. The automatic way was using the relax module, which is what was using Diego last tutorial. So right now, but I told you we are not saving anything. Let's save the data so that how to do. So we want to save, for example, if you use the finalize keyword, we will print, for example, the final stress tensor, and we can take the dynamical matrix, which is this object of the minimization, which is the final one, and we can say save QE and save SHA final, for example. And now, in this way, if we rerun it, we will say we will have the final data. So these things that you see here is because at the beginning, since we have only 10 configuration here, the step which is doing is too big because it's very random with only 10 configurations, and it's going so far from the correct position that it's getting imaginary frequency, and so you get this imaginary frequency and try to reduce the step until it doesn't find any more imaginary frequency, and then from there goes on. And the code does all of this very really automatically without us caring or crashing, and we have the final SHA results, so we can compare, for example, the frequency at gamma of the SHA results with the frequencies of the starting points, which are very different, actually, especially this low one. And and you should iterate this. So now I want to give you an exercise to do. Is you can reuse the same files. So I mean, you should have maybe something that is here. There is a plot. Let me see what it's doing. Yeah. So you have a plotted file, which is actually plotting the band structure. So let me run this plotter. Okay. So this is the harmonic phonon dispersion. Now my exercise here is try to modify this file and plot on the top of this phonon dispersion here the one you get with the SHA. So I will give you some moments to try to do that yourself, and I'm here to answer for questions. Yeah. Yeah, maybe.
Yeah, you need to do the Python. You need to do the Python script.
There is written in the if you look at the PDF, there is written.
Yeah, you go down.
So I mean, I don't know if the seed was working or not. So don't trust too much. So the output file is not so sure, but it is just to show how. Yeah, yeah. That seems very nice. Yeah. 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 In the last PDF, the one that you got, yeah, because it was disappeared. If you go in the school website, you find the video. So the latest video is on the SSCHA school website of the tutorial. So we fix some error, and also one of the scripts that is provided here.
Where is it in school?
Website is under lectures. No. Yeah. So there is the script. Actually, if you go to the SSCHA school webpage, which is so this is the website of the SSCHA, which is SSCHA.eu. If you go in schools 2023 and you scroll a bit down into tutorials, there is this section here, and here there is the new PDF with all the data, and in particular the one that is about our hands-on session, which includes all the scripts fixed, is this one here. Here you see all the scripts. This is the first one session. So if you go to the second one, this is the first field. Okay. So if you go to the second one, here there is the one to plot the data, how to force the positive definite. So all these things are commented that I just said to you. The ensemble generation, the file to generate the ensemble, how to do the simulation. Then you see the scripts used to generate the quantum espresso files. So all the scripts and the script to read the quantum espresso files fixed with the correct -A3. And the script to do the free energy minimization. This is missing, I think, in the version we sent to you for some error that disappeared from the PDF. And I mean, here there is more these 2 lines extra, which I've not included, which are required to save the data and plot the data with the SSCHA plot data, which is what you did also in the previous one. So if you want to plot the data, you should add these 2 lines, which are actually telling where to save all the data during the minimization. can actually do that. So we can actually do that. So we need to import also the utility modules, which is here. And then here we need to tell where to save, which in this case is minim, let's say _1 because it's related to the first population. And then to allow it to save, we need to pass to the run file to execute a method which is going to save everything at the end of each minimization step, which is custom function post. This function is going to be called each time we finish a minimization step, so you can have it. So you can customize a bit how the minimization works. In this case, is ioinfo.custom function post, which is coming save all. This is a function that saves everything. If we rerun it, this time we can plot the data of the minimization. Now, the free energy is increasing because we have a too little number of configuration, and this is not very good actually. So, so you can already understand from this plot that probably the number of configuration is too little because free energy is increasing.
Eventually this can happen.
Yeah?
Because we are going through the gradient. So if the gradient, the error is so big that you are going down in the gradient, eventually sometimes even if you go down in the gradient can even increase. So this is why you are going down. Yeah. But if the free energy is
if the free energy is increasing, it means that there is an inconsistency between energy and the gradient, and this is a signature that the stochastic ensemble is little.
Right. So it might happen that the gradient goes up in
yeah.
minimization. This might happen because if the structure is going down to a minimum that is more, what do you call it, more steep going down, the gradient is, as you go down in the free energy, the gradient can, the absolute value of the gradient can increase, but the frequency should go down.
So this is a good indication that 10 is not a big enough number of configuration for HTS. G extremely normal. So you should use more than 10. It depends.
It depends. Yeah, this is the question that everybody asks.
It really depends. I would say I would go with 100 at least, and then from there see. Probably for HTS 100 is good.
Even less.
Maybe even less. Maybe 50 should be already good. I mean, 10 is really too little.
So the story is if you are going to recalculate very often the ensemble, so it's better to start with something small, and then in the end you're going to increase it. But obviously, if you see something like that, it is a bit suspicious.
Okay.
How's it going?
I don't
So some hint, we should modify this plotter file. I think all of you realize this to get the phone dispersion. And what we can do is to load the dynamical metric, the final dynamical matrix here. So for example, with din SHA equals cc.phonons. So like we did for the harmonic one, phonons.phonons. And how did we call it? Let me have a look back to this. Was SHA final in this case. So you should call SSCHA final. And this is still 3. So now we loaded also this one. And then this method here, these methods here are just from here. I mean, I can underline. So these methods here are actually from IASC using the ASC DFE key points utility, which is actually giving a k path just in lines. It converts it in a band path in the brewing zone. So with this trick, we get the Q path, which is just an array of Q points in this path in the brewing zone and that many points. So these are the points in Cartesian space in the brewing zone. And then with this trick here, we are getting, if we want to plot the dispersion, what is the corresponding x point in a linear plot for each of the path. And this is x labels is simply the labels of the dispersion and where they should be in the plot. But what actually is doing the trick of computing the frequency, or interpolating the frequency in the path is this line here. So it's force tensor. You will see more this module tomorrow when we speak about interpolation. I think Raffaello is going to speak a bit. And get phonons in Q path. We pass the dynamical matrix and the Q path, and it gives an array of frequency. Yes?
That's similar to interpolation of quantum expression.
Yeah, it uses very similar subroutines. I think maybe some of the subroutines are actually the quantum expressor subroutine, which we converted, which we compiled to in a shared library that can be used in Python. So we steal a lot from quantum expressor source code inside the SHA. So this is exactly doing what MatDin is doing in Quantum Espresso, but you can use now in Python script like this, which I think is nice. And then this is simply doing the plot with matplotlib. I don't know if all of you are familiar with matplotlib. So this is what actually, for each frequency, we are plotting that frequency in our whole x-axis in red in this case. So maybe how to plot the other data is just adding one line here. And this is just plotting vertical lines for doing the plots. And if we go down a bit, we see that we have the ticks. We set where to plot the x labels and what are the labels. So instead of plotting numbers in the x label, we plotted the actual representation of the high symmetry points in the brewing zone. And that's just save the figure, so we can, even if you're working in a cluster, you can then pull this figure back into your computer. And so to give you finally the solution, it's simply like x.plot. Sorry, before doing this, we should compute the frequencies, interpolate the frequency of the SHA dynamical matrix, which is SHA equals c.force tensor get phonons in Q path, and this time is going to be yes. So din SHA and the same Q path because the cell shape didn't change. If the cell changed, the Q points change also. You should also recompute the Q path, passing the unit cell of the new structure. In this case, they are the same because we did a fixed volume calculation. And x-axis, and then freq SHA double dot This time, let's do them. Let's do them in red and the previous one in black, so that we have the red, the SSCHA ones. And just to distinguish even more, let's do these in dashed lines. So, oops. Okay, so let's try to run this plotter once again, if I didn't did a mess. And you should see one over the top of the other, the SHA frequencies and the harmonic frequencies. Now, SHA frequencies are always positively definite because they define an ensemble. So even if the system is unstable, you will see positive phonons in the SHA one. And tomorrow, Raffaello will explain the theory on how to actually detect instabilities with the phonons. So the auxiliary phonons are not the good phonons to look for instabilities, because they will always be positive definite by definition. And this is one of the big misconceptions that there is in the world of anharmonicity. So I think we can go on. I hope all of you catch up to this point. And now, this is very boring if you want to run a simulation all time, generating the ensemble manually, submitting calculation. I skipped something. I skipped the part in which you take all the input file into a cluster, prepare submission scripts in the cluster to run the data, submit those data, and then submit those calculations, wait for the cluster to end, and copy the calculation, the output file back, and then, do what we did with the output file to continue to run. So if you need to do this for each population, this is extremely boring, and it's doable, is what was done a few years ago for all the SHA calculation, but right now we have, as you see, ways of automatizing everything, and there is a way to interface automatically the SHA code with a cluster so that you can do automatic submission in the cluster. So if everything works in these things that we gave you at the beginning, that you should have a username, so a user number and a password written here, and these are key to access to a cluster, which is a local cluster open just for a few days for participants to the school. And so we can try to connect to this cluster with SSCH. Then your username, in this case, my one is user 11, you use your own. And then it is a key. You find the information on this in the appendix of the let me zoom so that you can see it better, I hope. So this is can be found in the appendix of the PDF. There is written the instruction on how to connect. In this case, is akey.cfm, which is building.ehu.es. So if we do like that, we ask for the password. I just type my password. I think I made a mistake. Okay, so here's my password. So is So I think most of them are, and now we are inside. So this is the cluster. Try to connect, and so now we will set up something to do an automatic calculation on this cluster. And so to do that, let's get out of here. And we have a script which is run cluster. Let's modify this script here. And now you have in the end of the, if you take your PDF, let me show it to you. If you take the PDF, you have an appendix, which is the last chapter, and the appendix is, you see there is this is the actual location, EP location of the cluster. And what you can see from here is that here is specified all the how the cluster works and is done, and how to connect, and an example of batch job. And so you will now use this to write the SHA code that automatically do the submission in this cluster. And we will do things in such a way, so this is an example of script to run Quantum Espresso on the cluster. We will set up this in a way, such a way to run on this cluster. So let me exit from here and let's take run cluster. Oops, I have already opened it, I think, here. Yes, this was run cluster. What is this? Ah, okay, so, yes, no. So this is exactly the same as before. Now we have another file here. We are loading a module, which is Espresso Calculator. Let's see. Yes, we have this file here. So this is very similar. I think Diego showed you something very similar as before. This is how to initialize a calculator for Quantum Espresso. This is required to generate the input file automatically. So we specify pseudo potentials here. This is Quantum Espresso and the parameters that we want. Usually it's good to use disk IO to none, since we don't want to save the wave function on disk. We don't need them. And so this speeds up a lot the calculation and avoid us to have the disk of the cluster working without good reasons. These are just the input parameters that they are very shallow. As you can see, you don't use this in production. You should test properly the parameters. Here I have the K points. So be careful that I have to mention this. We are running with a 2x2x2 supercell. This means that the lattice, our Brillouin zone will be of each calculation in the supercell will be 1/2, 1/2, 1/2 of the original Brillouin zone of the primitive cell. So if you do a Quantum Espresso calculation with a K mesh of 8x8x8 in the primitive cell, in the 2x2x2 supercell, you must scale the K mesh as 1/2, 1/2, 1/2 of the original one, because it's true that the supercell get larger, the Brillouin zone shrinks. And it's very easy to understand this in one dimension, where the dimension of the Brillouin zone is pi over A, where A is the lattice parameter. So if you double the lattice parameter, the Brillouin zone gets cut in half. And so you need half of the point to sample the Brillouin zone. So this is nice, because that means that even if the supercell gets larger and so the calculation gets more expensive, we can have less key points. That's good, at least. And then we initialize the calculator in this way. Now, this is a bit different. If you can see, it's not an ASC calculator. This is a cell-constructor calculator, because I find that there was some bug in the ASC calculator, so I implemented one for cell-constructor, which allows us to work better. So if you want to use like Diego was explaining to you this morning, just run on the local, you can use ISC calculator. If you want to submit automatically to a cluster, you must use the cell constructor calculator, because of some more some bugs that is present in ASC. I don't know if the latest version was fixed, but I don't know. So this is how you have the Quantum Espresso calculator. Then we have a cluster file, which is the most interesting one, which configure our cluster. So now this cluster here is a different one. So I have an exercise for you. You should modify this file to make it work on Eki. This is going to be very difficult. Don't worry, we will modify it later together if you don't manage to. So this is another cluster, which actually I have also the name is cluster of my group. And you just have to import this SHA.cluster module here and specify here the host name. Now, in this case, since we have not configured the cluster to work with a private key, we must also specify our own password in this way. So adding a new keyword, which is PWE. This is very bad. Don't do that in real cases. And within my beautiful password. So this is saving clear the password of the cluster is not good. So how to circumvent this way of doing things is simply by setting up the cluster with a private public key connection so that you do SSH to the cluster without the need of digit the password every time. And so, but since we don't have maybe the time to set up in now, you can just pass the PWD keyword to the cluster object. In this way, we will use the password. So this will use an utility which is SSH pass that probably is not installed. So to install on the virtual machine is like this. And this should work also in Ubuntu and most of the distribution. So if now we do SSH pass, it should work. Yes, exactly. So now we are able to use this utility that allows us to establish a SSH connection with the password in clear, written here. Don't do that in a production script because just set up properly the cluster connection. Now we have a lot of information that are given in the batch file. So if we go back here, sorry, let's go to the appendix. So in the actual cluster, so we need to tell the program how, so all the information that are usually written in the submission file. This works with learn. I think, I don't know if all of you have ever used a cluster, but this is what usually in a learn cluster, how you submit a job. It's possible to hack a bit the code to work also with other different schedulers. It's not, we are not going to cover it here. Maybe ask us if you want. But so this is with learn. In this particular case, we don't need any, so here this is the partition, so we don't need to specify the memory, we can cut this line. We don't need to specify the RAM, we can cut this line. We don't need to specify the partition, but sometimes you need. In this case, we don't, we can cancel. Now, usually in a cluster, especially if big cluster, you have an allocation which corresponds to an account. You can specify this here. This cluster doesn't need it, so we can remove it. Now we have number of nodes we want to submit. In this case, one node is sufficient. If you want more nodes to allocate for each job, because your each quantum expression, each DFT calculation requires more than one node, you can change it here. Use CPU, you can avoid it. These are some custom parameters, which if you want some variables which are specific to certain clusters, in this case, we don't need them. I think we need only maybe this one. Let's see. So we need this end task equal to 40 because of how the cluster is done. So we can delay it and leave it like this. So end task equal to 40, which is what is telling this line here. So this depends on the cluster a bit, the options. So you can always use custom parameter if your cluster are different, require some specific options that are not common to implement in the interface. Then the important stuff. So the time. We want how much time we want to allocate for the calculation. In this case, probably 5 minutes are more than enough. Number of CPU, I think 40 is okay. Let's see if 40 is okay. So this is, yes, this is when we run, number of CPU is what follow the MPI run command. So in this case, it's 40 is okay. Number of pool, this is specific to Quantum Espresso. We can go with, depends on the, should be, should be a, the total number of K points should be divisible for this number. In this case, we have 4 by 4 by 4, so we can have 4, for example, and pool, and that's going to be. And then how many jobs we want to run. Now, in this case, we want to run 10 jobs in total. divided in only one batch. So this means that we will submit one job, so the batch size is going to be 1, and each job will contain 10 SCF calculation. We can play a bit with this. So for example, if we say here 10 and 10, we will submit 10 jobs simultaneously, each one with 10 calculations, so we will run simultaneously for 100 jobs, 100 quantum espresso calculation. Now, let's keep this to 1. So the cluster is not so big, so if all of us want to run simultaneously, we should all of us submit only one job, otherwise we fill the cluster and other people are not going to be able to run. So in this case, it's going to be extremely fast. And here we want to set up the home directory, which in this case, no, let's do the calculation in the Scratch directory, which is Scratch user, and then the word directory that we choose. In this case is H3S-SSCHA, and this is going to be Scratch directory. Then, I mean, this is something that we can leave. Is simply putting a set -x in the submission script, so that in the output we will see all the input and output command run, which makes easier to debug. It's not necessary at all. These are the modules we need to load to run the SHA. Now, this is a configuration for a different cluster. We can now change for this one here in particular, which works. So in which we just need to load a module. It's written if you go here. Yeah, this is the module we need to load. It's Quantum Espresso written like that, so we can do here. We don't even need to pull. So module load. How is it written? Is Quantum Espresso. So this depends on the cluster indeed. This is this cluster here, EKI, and then we need to export, I think, OMP numtrevs equal to 1. I think this also depends on the calculation. Now we don't need these things. Now here there was a setup to have a local Scratch, which in principle is good in some cluster. We are not going to configure it now. So we cancel all these things. We also cancel this active shell. And that's it. That should do the trick. This should be now configured to work with EKI. Now, okay, no, we need to change the host name to be the EKI one. So in my case, it's user 11 at then the EKI configuration, which is eki.cfm.ehu.es. So this is the command that you give after SSH to connect to the cluster. Now, if you substitute here your beautiful password, I will not. I will, and I will do in clear so that don't use it to do criminal stuff. Otherwise, I will pursue your. So. So I will.
Remember that you are recorded. You are being recorded.
This will be deleted. This account, I think something like tomorrow. So I should not have said maybe that.
I will give you a couple of days, okay, to try this account in this cluster. This is the local cluster we have in the group. So please behave. So try, use it, but.
Okay. So for the time, if you are looking this on YouTube, it will not work. So now we modified everything, and now we should have, let me see, how was it called? The run cluster, I think. So exactly. So now this, so you see this is very script which is very similar to the other one. So we get this cluster object from the function before. It's defining a different file just to keep this script clean. But to compute it, after generating the ensemble ensemble.compute ensemble, we use this function, in which we pass a calculator, which could be an IC calculator. If we don't pass anything to the cluster, the calculation is done locally, exactly how it was in the previous tutorial. If we pass the cluster keyword, now it will automatically submit everything to the cluster. Copy, generate all the input file, copy all the input file to the cluster, do the submission, and do everything for us. And we will do this right now. Let's see if I have not done some mistake. Yes, before going on, so there is, I think, something we need to do in the Espresso. In the Espresso calculator. So I've not specified the pseudo, where are the pseudo potentials. So we need to copy the pseudo potential into the cluster. So in this case, let's connect to the cluster. Do I have saved the SSH? No, maybe in this other. Yes. So, oh my God, ls. Okay, so we can create Espresso directory, Espresso, double S. And then inside the Espresso directory, we can create a sudo directory. And then we can copy, let's exit, we can copy the pseudo potential, which I hope they are here, let me see. Yes, they are in this directory, so we can copy all the pseudo potential into the cluster, which is, we can copy. So, Espresso, sudo, now we'll have to re-enter the password. So in this way, the calculation will now find the pseudo potential inside the cluster, and if I do Python run cluster, hopefully, wow, SSCHA doesn't exist. So we will use, yes, of course. So we need to start the SHA. So we can use din start population 1, for example. I think we can use this one. Okay. So there is a problem in communicating. I think it's, yes, it's my password is written wrongly. So is here. So now should be good. Let's see. Okay, so submitted. So here, this line here, after all this crazy printing, is telling us that he submitted the job on the cluster. So if we now reconnect again to the cluster, SSH user 11 at yes. Okay. Maybe I should have taught you how to configure the key so that no. Yes. So if we go here, hopefully it's still running. Yes, so the calculation is still running. And if we go to the Scratch, our directory, we have the HTS-SHA, we see the calculation which are running. So you can see that some of the, so the script automatically generated this script here, which is the submission script. which you can see has been generated with the parameters we say, so 1 node, 40 processor, this is the time, 5 minutes. We have not specified an account, so the account is left empty. Usually in this cluster is okay, usually in a different cluster you should specify the account if you have an accounting. We have not specified the queue system, the partition. This cluster doesn't require them. You can add, as we did with task, with the custom configuration, you can add your own custom configuration here to have more freedom in specify something which could be available only in some cluster. Then here are the module we specify how to load, and this was everything. In general, here in this load module part, you can put everything that requires to be run, so loading modules, essentially setting up some environmental variable. If you need something to do something else, it can be put here. And then here the software automatically goes into the working directory which we specify to be in the SSCHA, and then it's submitting. We said we want to do 10 jobs altogether in one only, so 10 different job number is equal to 10 with one batch, so only one job is running with the 10 configurations. And here you have the input file automatically generated and the output file which are running. Actually, I think it's finished. Yes, it's finished. So, to avoid spamming and keeping on the connection activated with the cluster, which is something that some cluster will kick you out if you try to do that. So, this script is checking once every 5 minutes. By default, it's possible to change this. So, it still have not realized that the calculation is ended, because every 5 minutes it will run a SKU for us. It will reconnect to the cluster, run a SKU, and if it doesn't see anymore the job ID that was submitted, it will automatically download the output. And so we can see which time is it right now. So it's in 12, so in 9, so we should wait 2 minutes. In 2 minutes, it will check again, realize that the job is done, and copy back everything. So if we add a new, so I don't want to stop it. So anyway, so you can see here, this is my file. So I will go out. Okay. So the cluster generates automatically the cluster work directory, which contains the input file of Quantum Espresso and and also the bash. So these are the files that are actually copied in the cluster. To do things more efficiently, we will not copy file by file, but we'll compress all the file in a tar archive, which is the last one, unfortunately written in red, which is not very visible, but is this one here, is a tar file which contains all these things and is copied. So the communication only occurs with this compressed file. So that is not compressed, but this single file, and then which is unpacked on the cluster to avoid to have too much communication. So this is what is going on, and if we see now, it should be done exactly. So it did everything, saved the results, and so you see printing a lot of stuff, which is mostly for debugging purpose, because as you can imagine was but he was able to think and he finished. So I don't know what's happening. I have no more the control. Okay. Okay, yes. No, the keyboard is not working. Let me close. Okay, I will open a new one. Okay, this works. So let me zoom. So we were in 02, no, in tutorials. Where were we? What was the? I don't know where we were. Documents, no.
What are you looking?
I had to restart the terminal, which was not responding anymore. Where were the directory of the tutorials?
In the desktop.
Desktop, okay, see.
Desktop, SSCHA.
SSCHA, okay, I see. So it's 02, okay.
Yeah.
We are back here. So if you now look to the ensemble, we have population 2, which is the population which has been actually run with the cluster. So this still seems to be very manual because the cluster only ran once, but now you can actually insert this cluster into the relax object that was introduced in the previous tutorial, and it will restart automatically, run the SSCHA calculation, restart automatically everything, and do exactly what we did with gold, but this time interacting automatically with a cluster. So you can try to do it by yourself in, I think, in the last 15 minutes. And if you have a question, we can go together.
So is the task clear? So this is actually this is the most efficient way of using the SSCHA. Right?
Yeah, so this is the most complex probably thing to do, and also the most efficient. So the most efficient way of running the SSCHA is actually doing it this way. So you have set up the cluster, and then you actually, let's do it together because it could be difficult. Huh? So let's modify the run cluster. Okay, now we did everything in this way. We can do the full minimization iteratively, and we can modify the script essentially writing exactly what was the input file of last for gold that we had last time, but this time doing everything automatically. And so we have to load the minimizer and the relax model, which is, I think, inside relax. Yes, should be. Okay, so here we don't need to compute the cluster inside the ensemble because the relax model will do it for us. So we need to just initialize the minimizer. So it's done like SSCHA minimizer. SSCHA. This is exactly what we did for the manual. We pass the ensemble. And now we have to define the relax object, which is what is going to resubmit automatically everything, which is SSCHA.relax.SSCHA. Now we need some parameters here. I don't remember them by heart. Let's just look. They are written, should be written, I think, in the previous tutorial. So yeah. So the first keyword is the minimizer. So is the minimizer. The second keyword is the calculator, the espresso config. In the last example was the AMT force field for gold. And now here is where things change because we can pass the cluster keyword and put cluster config in this case, and this means that the calculations are going to be submitted on the cluster automatically. And now we can specify the number of configuration. We can put maybe 30. Now we will move maybe 10, otherwise we need to modify also the other one. And the when to stop in case we never converge, which in this case we can put 2, so that things are going to finish in time. And then we can just call relax.relax. And that's it. And we can cancel all of these things, and maybe just here relax.minim, we can access to the minimizer.din.save QE just to have this way. And I think this should do the trick. So as you can see, it's very simple. You can edit this file almost manually. So most of the files that we see in are very, so it's not that long actually. So most of the files that you saw also in the previous tutorial contains a lot of line, but most of them are comments or fancy stuff to print things out correctly. But actually the actual relaxation, so these 2 lines here are what are setting the calculation to be restarted automatically each time. This one here is setting the minimization. So for example, if we want to reduce the gradient threshold, which some of you will need to modify parameters inside here, for example, meaning-full factor, we can put this to 0.001, and this is the threshold on the gradient required to reach the minimization. This is a property of the minimizer, which gets everything. We can change the conv-liu meaning.conv-liu ratio, which is the ratio of the effective ensemble size below which, this is by default 0.5, below which the system automatically is started. We can be a bit more gentle, and instead of 0.5, you can 0.2 for the beginning. You can play a bit with these parameters. These are all objects that can be set in the minim object, because it's what matters in the single minimization within one ensemble. The ensemble parameter specify essentially the temperature and the starting dynamical metrics, which are the information used to generate the ensemble. So if you want to change the temperature of the simulation, you need to change the temperature here. In this case, it's 300 Kelvin. And that's it. So relax, we can, is what is setting up this relaxation. So it needs to know how to compute the ensemble. So with the espresso calculator, it needs to know how to submit to the cluster if this keyword is known or is not present. It will run locally, like it was in the previous example. In this case, it will run on the cluster automatically. And then if you want to do variable state relaxation ablation, replace relax with VC relax. And that's it. And I think if we run this, we can try. Hopefully I've not done mistakes. So, yes, so what actually did is now submitting the first ensemble, and I mean, in 5 minutes you will get it back, do the sharp relaxation, submit the second ensemble, so on and so forth, and do everything automatically on a cluster ab initio. So, if you have questions, I can help you while it's running on the cluster. Yeah. Yes, sorry. Yes, maybe I was too quick on that. Huh? So let me. So this is the cluster.py, which has been modified with respect to the one that we gave you to be adapted to this particular cluster, so that we show how to actually adapt this file to the cluster. So these are the keywords. These are quite simple configuration. And so if you want to play a bit around with these, so you can try to do, for example, in this case, maybe if you can, since 5 minutes is really too much, because so in 5 minutes we are running much more, we can run much more than 10. So you can probably do 30 configuration and just increase the job number to 30, so that it allows to run 30 configuration in just one job, because it's very fast. And you can see that if you have very powerful clusters, you can use also a big number of batch sites, so you will have a lot of jobs which run simultaneously. And so you can actually do hundreds and hundreds of ab initio configuration all together. And this is a very good thing about SHA. So actually, with respect to molecular dynamics, in which each configuration to be run require to run all the previous one sequentially, because each new position of the atoms depend on the forces of the previous configuration. In the SHA, each So inside the same ensemble, all the configurations are independent and can be generated independently of each other. So the configuration within the same ensemble, within the same population, are all independent, and so it can be run massively in parallel and in an embarrassingly parallel way. So even even if the code you are using is not parallel, you could parallelize on the configuration. And then indeed, so the number of CPUs and the number of pools is what is telling Quantum Espresso to run in parallel itself. So we are doing, in this case, it's not in parallel in the configuration because we're only on one batch size, but if we have many jobs simultaneously and then many CPUs together, we can exploit the actual big size of cluster of tier 0 systems that is a very big cluster that we have access to sometimes if you have project on them.
Could you please show the run cluster that you have just defined?
Yes. Not here. I will open a new one. Oh, this one here. So it would. Sorry. Yes, let's try. Maybe in this way, yes. At least there is the password. My password is covered then. In the case you have not yet do some criminal activity with my account.
Do you have a maximum number of jobs that you can submit in your cluster?
You can use the batch size. This is the number of jobs that are submitted.
Yeah.
So if you use this in the limit, indeed, if you run more SHA calculation, you should be careful because each SHA calculation will only care about its own jobs. So you must track how many.
For example, you have 200 maximum, but you actually have 400 population. Is there a way to tell the script?
So you have 400 configurations and 200 jobs.
Yeah.
So the best thing would be to run the batch size something like 40,
yeah.
and then run 10 job number. And so the total number of calculation will be is this times this, because each job will run 10 jobs.
But the drawing is more complicated. So imagine that your job fills up the maximum time in your cluster.
So you want to run only one job?
Yeah.
Okay. So you can use a batch size which is smaller, and in that case, the system, so this is also true if some calculation randomly fail, what is happening is that it will continue to submit until all calculations have been completed. This is also true if some calculations fail. So if you put here a number which doesn't reach to the maximum number of jobs, it's fine because you will submit before those jobs, but then when they are finished, we'll check which calculation has still to be done, either because they have not been submitted or because maybe failed. Sometimes happens that you submit on a node that has a bug or has some problem or is drained or something weird happens and the calculation fail on that node, and so it will realize that it will try to read the data. If it errors, it will try to resubmit them. The resubmission of each job will be done up to 5 times. This number can be changed, and if it fails the same calculation for more than 5 times, the job errors and the exit saying, look, something is weird with your input files. I'm erroring too many times, and probably there is a bug. Either you didn't put the pseudo potential, that's something that happens, or maybe it's a very weird system in which you have atoms too close. There is or I don't know, something. So, but in general, it's very robust. So even if the cluster fails, it will resubmit things automatically and do a very automatic stuff. let me see if it is already finished. So you can see here, one of the calculation has been finished on the cluster, and it's running the SHA minimization. So it's doing everything automatically. Then when this finishes, this was the first one, it will submit automatically a new population to the cluster.
So it's running the minimization in the cluster?
No, the minimization is running here. So it copies everything in the cluster, then run the minimization, recopy back things, and run the minimization locally.
And why you didn't run the minimization in the cluster? You did only one processor for the
Yeah, because usually, so the minimization itself is not parallelized right now in the SHA. So if you run on 10 processor or one processor, doesn't change.
Yeah, but you can run it using only one processor.
Yeah. You can also, you can hack a bit these scripts. So if you go back,
Instead of going back from the cluster to the local computer.
yeah, you can hack a bit the script and put here localhost and do in a way that this will automatically submit on the on itself. You see. So if you just put localhost in the host name, I will cover my password. And so sorry. This one and this one. Okay. So if you put localhost, it will submit on itself, and then you can actually run the minimization in the cluster and everything locally. It's a bit of an hack if you want. So if you want, usually this is taught that you have your local workstation, which is doing everything and just connecting to the cluster and making the cluster work only on ab initio stuff. If you want to run everything on the cluster, what you can see is that instead of host name, the connection of the cluster, you can replace here with localhost, and it will actually try to submit to itself. So you can run on a cluster like it, you can connect to a cluster which is localhost, which is itself, and it will submit on itself. So you can actually hack.
So you're running everything on the workstation.
So this is like running, so this actually is running here, but then it's copying on the cluster the ab initio file and running all the ab initio data on the cluster. So this is running here in this case, and then just copying to the cluster the ab initio file. If you want to run everything on the cluster, put there localhost. Yeah.
So when I SSH cluster code, I first need to access some other computer, and then from there I access the cluster.
There is a trick which is using proxies. So you can configure actually the cluster connection. So I don't know how to do it here because I don't have a cluster to do that here. But if you go into the SSH, there is no, but you can create a configure data and then configure your connection to a cluster so that you do a proxy jump to another one. If you look to proxy jump SSH, you will see how to do this. And in this way, you can do SSH to something, and it will automatically under the hood do these things for you. So then in your host name, you put what you have to do the SSH in one step, and it will under the hood do this for you. Or you can open a tunnel, but I mean, there is a bit, so you can look to the SSH option to do that. Let's see. It ends, so you can see that we run actually an ab initio calculation on H3S in a few minutes. I mean, it's not converged because it was just 10 configuration, but probably you could have done in 50 configuration, and which would have been enough to do something. It was a very small supercell, the 2x2x2, but if you go in a 3x3x3, probably you can still do it in a reasonable amount of time. And this is an example of an actual calculation that with very few effort can be moved in something which is helpful which is actually a calculation which could lead to data which are publication quality, and so on a real system. So you can see here we have final SHA automatic, which was the result. So in 10 minutes we had it. So you will see that the data actually automatically save. I think is not in this case because we didn't specify. So no, in this case not save the ensemble. You can specify in the relax save or lock ensemble. There is a keyword we can look online in the documentation, which allow you to save the ensemble so that you don't, so that you can then redo the minimization and analyze further the data. In this case, I've just rewrote it myself, but probably in the tutorial, let me see if it's written.
Can we use the same relax object? Can we use the same relax object after the relaxation to continue this variable?
Yeah, exactly. Yeah, you can also change the number of configuration, the maximum population of the same relax object to do first a relaxation with a few configurations. So you can actually, let me show it to you.
And it will use the last dynamic automatic.
Yeah, so here, after this relax, you can actually modify something. So you can do relax.nconfigs equal to now 1000, for example, and then again relax.relax, and it will do, you need to maybe update the max population. I think it's max pop, you can see in the tutorial. This was 2, now it's going to be 3, and if you do relax.relax, it will continue. So
maximum population is after continue and all.
No, this is he knows which is the current population. So if he arrive to maximum population equal to 2, then here population is equal to 2. So you need to increase, otherwise the maximum population is the same. I think that he will anyway do at least one population. So in this case, it doesn't matter really. But if you want to do, let's say, a lot of more calculation to be sure to be converged, you have to increase a lot this number. You can also change the temperature here and redo a relaxation. So if you want to do a relaxation several temperature, which is very similar to what Diego showed you before with the thermal expansion code, you can do whatever you want. So you can hack a bit the script to do different. So you can also do, for example, here a relax time VC relax. So you do first a relaxation of fixed volume in which you arrive close to the minimum, and then you allow the system to relax the cell to avoid to go to strain cell if you have a very crazy starting point. So this is more efficient. And you can a bit play around with all these parameters. Since this is a Python script in the end, this is a bit more flexible with respect to the input file of Quantum Espresso, which is one kind of calculation because you set up those parameters and those are. This is a Python script, so it's something which is dynamically running. So you have a bit of freedom in working with these kind of things.
Can we do such things with not Python script, but with input file?
So there is also a way to run the SHA with input files. We are not presenting now in the tutorial, so there is actually, but you can configure the cluster calculation automatically. There is actually a namespace. So if you go to the website, actually I think, no, I don't think in the website there is. So I don't know where we could find an example of it. So maybe we should update the documentation to put an example of it. So we don't, since the Python script are so flexible, we usually use Python script input file. It's possible also to use static input files. There are, I think, some example in the website. So if you go to the SSCHA school, here you go to the tutorials, I think that this tutorial here has some examples. So this is the Python script. So exactly, this is an example of how to run a SHA calculation with an input file, which is very similar to the Quantum Espresso ones. And so you have population, where are the dynamical metrics, supercell size, temperature, some option of the minimization, UTs if you want to save the frequency, and you run the code with the SHA minus input command. So there is a way of running the SHA in input file which are very similar to Quantum Espresso. But this is actually, this SHA executable is nothing less than a Python script, which is loading this file and setting up the variable exactly like we did directly in the Python scripts and running under the hood. So it's just a matter of what you prefer to do. So if you're more used, there is the way.
You can, so I create my own input file for the parameters I want to change, and you have a preamble that reads those variables.
For sure.
It's very easy.
Yeah.
Are you managing to submit jobs and run the cluster and so on? Some say yes, some say no. Or
What is the problem?
I get bugs at the beginning, but
So
I probably have to just like it's going fast on the screen, so I will have to go back to this after this.
so I went too fast.
yeah, it's
Sorry.
fast, yeah. So maybe I mean it's already almost 7:15. So I guess the best thing we can do is
So anyway, you have in the PDF, all these instructions are written. You have the input file, most of the input file you have them. So you can try a bit yourself. The cluster actually, which is not written in this thing here, it's in the appendix. There is actually a cluster configuration that works with Heki. You can copy that one that was done by Diego, like, thankfully. And so in the appendix, you have actually the solution of the cluster script. So you can come back to it, and these accounts will remain open, I think,
the whole week. Yeah. So
the whole week. So you can, and this is the only actually time that you need them. So. Okay.
If not, you can always go to the manual submission.
Yeah, I mean,
It's very boring. But,
it's very boring, but
I mean, we've been running the manual SHA for all the time, but in the last couple of years. So, primitively.
now I have to say that there is also someone in the audience that is probably going to work on it. We are working also to do I'm announcing beforehand, so I probably shouldn't, but we are probably going to do also a collaboration with AIDA. I don't know if some of you know about it, and to have the possibility to use the AIDA expertise to managing clusters and cluster submission, which is another library, which is very good to use also. So all this is implemented automatically with Quantum Espresso. You should modify the code and do a bit hard code to, if you want to use VASP with this automatic cluster submission or other softwares, because this is implemented all for Quantum Espresso. It's not probably too difficult, but so thanks to this collaboration with AIDA, probably we will be able to have a common workflow for all possible, most of at least programs, including Abinit, VASP, Siesta, and most of them, which will be which are already implemented in this stuff, but it's not yet ready. Yeah. It's you can interact with this kind of thing. So.
And in order to configure the cluster, we need just to make a file with unpublished.
Yeah.
Which is in the appendix.
Yeah, that is a way, of course. So this is the file actually. In the appendix, you should maybe just modify the things. So in the appendix, there is a working cluster. You should just adapt the two things to work together.
For example, if I have one file like that, and I just encrypt it, and I then just run the
It should work.
run clusters, it should work.
Yeah. Yeah, because this, you see, this configure cluster, this script is creating this function configure cluster that returns this cluster here, and this is called in this other here, cluster.configure cluster. So this line here is calling this other script, which is called the cluster.py. So if you modify this file here to be like that, then this one here automatically will be this one. So this is just a way to having things ordered, so not to have all the espresso data and the cluster data in the file that runs, so that you can see this in one screen. That's okay. I think it's quite late. Anyway, this is it's being recorded, so you will have it. You have all the data also in the PDF. Most of these files you have already in the files we distributed. So, I mean, as you can see, I did it manually now to modify these things. So, once you get a bit of use of it, it's becoming. So maybe the first time is quite difficult, but then it's going to be easier and easier with time. So, thank you for the attention.